This video is about resistors as physical objects. It corresponds to section 4.4 of the Applied Analog Electronics textbook. Now, there are two types of resistors that you will encounter. One is the surface mount resistor, and that you'll see on boards like this one. This tiny rectangle here, not the bigger one next to it, but the little one, is most likely a resistor. And there's a couple other small rectangles here that are probably resistors, and possibly this little one here also. The bigger rectangles are probably capacitors. One of them might be a diode. It's a little hard to tell these tiny components apart because they're not labeled and because they're really, really small. And so we will not be using surface mount components for most of what we're doing because they're just too hard to work with, particularly if you need to be changing resistors, measuring them, deciding, hey, I didn't want a 10 kilo ohm resistor there, I wanted a 22 kilo ohm resistor. Changing them when you on a surface mount board, really difficult. So we'll be using what are called through-hole components. This is an older style, and you can see they're very much larger. I mean, it's bigger than the pins on the board. But they are easier to work with on a breadboard. You can do what I've done here and just bend the leads over and stick them into the breadboard. And you can also lay it down flat against the breadboard. You can also read the value directly from these bands of color that are put on the resistor. And coming down from the top here, I have got, let's see if I can point to this, brown, red, black, black, brown. Those 5 color bands there tell me how big the resistor is and how precise it is, what the tolerance is. You can sometimes also, if you get them in an assortment like we did, get a label here that says this is a 120 ohm resistor. Those labels aren't always right though. And so it's a good idea to double check both, is it consistent with the color code, and you can check with a ohm meter to actually measure the resistance and see whether or not it's correct. Though the ohm meters that we have for this class were the very cheap ones, the handheld ones, and they are less precise than the resistor itself. So that if you get a number that's just a little bit off, the meter is probably what's off rather than the resistor. Okay, let's take a look at that color coding a little bit more carefully. There are 10 different color codes that correspond to different digits. There's also a couple other ones that are used only for tolerances. The colors are fairly easy to remember if you can remember the rainbow, because it starts with black and brown for 0 and 1, then it goes through the rainbow, red, orange, yellow, green, blue, violet for 2 through 7, and then having run out of rainbow colors, it goes to gray and white for 8 and 9. And those color codes on the bands, there were 5 bands on the resistors we were looking at. The first 4 of them encode the value, and the 5th one encodes the tolerance. The first 3 digits are just numeric digits. So we had, I believe, brown, red, black as the first 3 color bands. And that's a 1, 2, 0. That's 120. The next band is an exponent for a power of 10. It was black, so that's a power of 0, that's 0, 10 to the 0th is 1. So this value was 120 times 10 to the 0th, or just 120 ohms. So this was a 120 ohm resistor, and then we had one more band which was brown, and that corresponds to a tolerance of plus or minus 1%. Plus or minus 1% resistors are probably the most common of the through-hole resistors these days because they're very cheap, metal film resistors, and 1% is usually good enough for anything that you're likely to be doing. You can get more precise resistors, you can get 0.1%, you can even sometimes get 0.05%, but those cost more, quite a bit more. You can also get still available some worse resistors, some ones with 5% tolerance. These are usually some sort of carbon composite rather than metal film resistor. They're harder to make precise, and so they're usually only made 5% tolerance. Some of the older ones, if you go back to looking at equipment from the 50s and 60s, you'll see 10% and 20% tolerance resistors. The manufacturing standards then were not as good. But they're not used as much anymore because they really aren't any cheaper than the metal film resistors. So you'll see them occasionally, but the difference in price is so small that just about everybody's using the 1% metal film resistors these days. Okay, there's one minor problem with using 1% resistors, and this is due to what I would consider a bad design choice in making up the color code. If you notice, the 1% resistors use a brown code. Well, if you look at the 5 bands on the resistor, which end is the tolerance code and which end is the first digit? If I've got brown, red, black, black, brown, that was the 120 ohms. But if I read that in the wrong direction, I would get brown, black, black, red, brown, which is also a legal color code. That's 10 kiloohms. And 10 kiloohms is at least as common as 120 ohms. So it's very hard to tell a 10 kilo ohm and 120 ohm resistor apart. Basically, you have to either measure it and say, oh, yeah, this is 120 ohms, or something that I find useful is that when I'm doing the sticking them into the breadboard, here I've stuck them in so that one end's on top and one end's on the bottom, and I always make it so that the tolerance band is the one on the bottom, so that I can always read going down the resistor. And that way I can read the resistance as long as I haven't bent the wrong lead of the resistor without having to go back and get a multimeter. That's useful because the reading with a multimeter often does not work if the resistor is in a circuit, because the effective resistance of those two between those two nodes in the circuit is not necessarily just the resistor that's between them. Okay, so what resistor values are there available? Well, you could get, theoretically, any resistance value, and people would put color codes on it, but manufacturers don't want to have to make an infinite number of different resistors. And so there's some standard resistor values that are used. And let's take a look at those in a little table here. There are different series. The E6 series has 100, 150, 220, 330, 470, and 680. So the numbers that are in the E6 columns there. The E12 columns has those, but ones in between also 120, 180, 270, 390, 560, 820. There's also an E24 series that divides them even finer, and an E48 series which divides them even finer and in the process adjusts a few of them a little bit to be able to make them a little bit more closely spaced. And we can take a look at what this resistor spacing scheme is all about, because if you plot it with the resistance on a log scale here, then you can see that the spots for E6, for E12, for E24, and E48 are uniformly spaced. They're uniformly spaced on a logarithmic scale. That means the ratios between them are roughly constant. And the E6 series was chosen to make those 6 per decade. And E12 has 12 per decade, E24, 24 per decade, E48, 48 per decade. And so you have evenly spaced ones across the entire range, and they continue past just the 120, 100, and so on that was here in this chart, because I can multiply these by any power of 10. So when I'm saying that E6 consists of 100 and 150, that means it also has 10 and 15. It also has 1 and 1.5. It also has 1 mega ohm and 1.5 mega ohms. Any power of 10 times these numbers will produce something in that series. And so if we look at the spacing here, it goes each decade looking the same. And the reason that the E48 had slightly adjusted numbers, if you look at the E24, you can see that the spacing has started to get a little ununiform here. Right there, you have 4 and then a little bit of a gap, and then 2 close together, and then a slightly bigger gap. Those slight gaps are sort of annoying if you're saying, well, I want a value that's close to this. If you wanted something in the middle of that gap, it'd be a little annoying. You'd have to go to the E48 series instead of the E24 series. Incidentally, there's an E96 series as well. And depending how much tolerance you need, how precise you need to be with your values, you can pick different series of values. If you can get away with, I just need an approximate value, I don't need to be very precise, then the E6 or the E12 series are by far the most commonly available resistors. And so we generally use those when we can. If you're looking for 1% precision, and you really need very precise values, you may have to go to the E48 or even the E96 series. We will not need that sort of precision in this class, even though we have 1% resistors. We're not going to need most of our values to be as precise as the resistors are, so that you can easily get away with using just the E24 series for everything we have to do. Okay, I think that's about all you need to know right now about the physical resistors. There is one little trick that is worth doing. You saw previously we had these little resistors on pieces of paper. This is designed for automatic insertion of resistors by machines. It turns out that those pieces of paper and stuff get tangled very easily. They're very hard to work with if you've got just little snips of them like that. And so I find it useful to put the thing into a Ziploc bag. Label the Ziploc bag with the values, and then have an index card box. Lots of different resistor values in there. You'll probably want to find some way to organize your resistors so that they don't get all tangled and confused, because it can take a long time if you've just got a pile of resistors and say, oh, I want 120 ohms. Well, which of these 50 different strips of paper is it? Do I even have 120 ohms in there somewhere? Putting them in order somehow makes a work in the lab a lot simpler. Okay, that's probably it on physical resistors. We'll talk more about resistance in a subsequent video.